Hello and welcome to the webinar of Würth Elektronik ISOs. My name is Eleni Stark and I will moderate the webinar today. We are very pleased that you took the time to participate in our webinar. Our speaker today is our field application engineer Timo Dreyer. He will hold today's webinar on USB 3.1c, technical analysis and design tips, and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you can't ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You'll find the chat function in the webinar control panel. Please also indicate the slide number from the presentation in your question so that we can easily relate your question. The slide number is located in the right corner and top of the presentation. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 15 minutes in addition scheduled for this. If we can't answer all your questions within the 15 minutes, your questions will be answered by email following the webinar. The recording of today's webinar will be available one day after the webinar on our website within the navigation point Webinars. Now I'm giving directly to our speaker, Timo Dreyer, and I wish you an exciting webinar.
Hello, my name is Timo Dreyer, and I will be the FRA for that topic today, where we speak about USB 3.1c. And we will have some technical analysis, and I hope that I can give you some design tips. So before we start, we will take the time to have a small look about the summary. At the moment we have some, is that okay? Yeah, it works. Let me check. Okay, now it works. So here we have the table of content. So I like to give you a little bit of history about the USB, because to understand the history and the evolution of the USB types and connectors helps us to understand why the connector type C is really a special connector. And after that, we will analyze the main characteristics of these connections regarding the electrical performance, the mechanical performance, and also the RF behavior. And after that, well, everyone can finalize his own answer and what kind of application it might make sense to use this kind of connector. So when we start and when we analyze the market first a little bit, we will see that this is really a fast-growing market where we have a lot of potentials in that market, when we have these tablets and laptops and also desktop computers in our mind, and that is a reason why the USB 3.1 gets more and more popular and more requests about using that type of connector. What we did is we analyzed the needs of some customers or of a lot of customers in America. What did they expect from a Type C? And what you can find here in the table, that's the list of the top answers what we got. So higher durability, higher data rate, and also regarding the power supplies, it is a growing need. And there we already recognize that we have to combine different features in that type that it fits to our needs in our applications. When we jump back a little bit to the history of that type of connector, we will see that this was launched at the market in the year 1996. 2 years before, so in the year 1994, it was started from some industrial leading companies like Intel, Microsoft, Compaq, and NEC. And they were looking for an industrial standardized connector, USB Universal Serial Bus, so one type of connector what everyone can use. And this is important to understand, that that design of that type of connector was really made for an industrial application. Today we know USB mostly from the consumer market, but all the requirements what we need in the industrial applications get covered by the USB. So how was this process, how was the evolution, and what was the need of that type of connector? So the need was, after the years, to increase more and more the data rate. And that's exactly what we can see here. So the name was changing also from USB to high speed to super speed plus. Why? Because the data rate gets more and more increased. And with every evolution step, well, one main target was to be backwards compatible. But that doesn't work for 100%, but in the most cases. When we analyze that a little bit, we will see in the year 2000, USB 2.0 was launched, and they are very famous is the Type A and the Type B at the market, what we know from the different devices. Type A we have mostly used for a master device, for a computer, things like that. And the Type B was mostly used for a slave device, for a printer, for a scanner or something like that. So there we had these 4 pins, and with the first evolution step to the mini and micro type, we were adding 1 pin. So from 4 pins, we were jumping to 5 pins. Why? Because we have to use the OTG identification, what gives a signal which device plays what kind of role. So let's take that example of a camera. When a camera, for example, is connected with a computer, the computer is a master device and can store or delete maybe pictures on our camera chip. But if we connect the same camera for a display, well, in that moment the camera is a master and the display is a slave, because the master tells every time the slave what he has to do. So to figure out in what mode we are using our device, we need this OTG identification, what we can see here for the mini and micro with pin number 4, to figure out, okay, in which role do we use our device. The next evolution step was in the year 2008 from 2.0 to 3.0. So what happened there? The target was to increase the data rate, and like you can see in the bottom line, that we have really increased the data rate multiplied by 10. So that was a really big evolution step. And because of the size, the mini connector was deleted and not really existing at the market anymore. So the target was to increase the data rate, and that what we can see multiplied by 10. How does that work? Well, there are different ways how you can realize that. And one main point is with more data lines. It's similar like when you like to drive to downtown and you will arrive in a traffic jam. But, well, if the road is bigger and you have more lines, more cars can drive into downtown in the same time. And here it's the same with the data. So more data lines means higher data traffic, what you will be able to handle. And the second point is we have to, well, when we still keep our illustration by driving into downtown, a second way is to arrive there faster, is to drive faster. So increase the speed limit. And here it's the same. But to be able to do that, you have to protect the data against EMC. And so the shielding got more and more important with that evolution step to the 3.0. But the result was pretty good. So here we have an example of a 25 gigabyte Blu-ray movie to record that. And that was a high evolution step. When we take a look at the example of USB 1.1, more than 9 hours, and now we are in around 1 minute be able to record that. And well, when we take a small view about the protocol and the architecture, we will see that here we have a TX and RX signal, what can be sent and received from both directions. So that was also included into the USB 3.0 signal. So that was an additional benefit of that. Regarding the time and higher speed, is that chart very important to understand, because in total the total power what we need to transfer that was reduced. But how is it working? And that is what we can see here in that graph. We will see in with the red line, we see the active signal, and what happened is there was an increasing of the height from 2.0 to 3.0, but the time was reduced, and that gives us the opportunity to transfer faster, more, but with less power in total. So the next evolution step was 3.1, launched in the year 2013. And well, what did we learn? We learned we can increase the data rate by increasing the pins or by a better shielding. And here the pins are the same. So you will not find a difference between a USB 3.0 and a USB 3.1. For example, for the B type, it looks similar, but the shielding was better performed, but the pins stays the same. But then we were reaching the really new type, the C type, where we will focus now in that presentation a little bit on the C type, what you can see here, what is really the smallest type of connector. Okay, what you can see here is the pinning, and you will find in the table the graph of the different power supplies, what every pin is able to handle. And here we can see that they are distributed, so they don't have all the same current rating what the pins are able to handle. So 0.25 amps is for signals, that's the maximum rating, but then for the power delivery mode, up to 5 amps we are able to handle with that pins. Well, this is the electrical performance and how much current we are able to handle. But what about the other characteristics? When we take a look at the mechanical performance, also the rules of the USB organization changed, because for the C type it was recommended to handle 10K mating cycles. And that was a defined insertion force and with a defined extraction force. And to be able to handle that with a Type C connector, even in that size, there's also the test performance from the USB changed. What you can see here is that the first time we make a test after 1000 mating cycles, and the test result has to be the same after the maximum mating cycles of 10K. And that already explains why, regarding the mechanical performance, we are really speaking here about a high-tech connector what is able to handle that. How is it possible? Well, it's every time a summary between the plug and the PCB side, and the structure has to be in a way that there we are able to handle these forces. And one way to handle that, we can see here in that graph that we have these that we are working with these kind of flanges, what we can see here. And that's important when the PCB gets soldered to it, that we can absorb the mechanical forces by a correct housing design. But that's something what we have to keep in mind when we are designing our housing, that we have to design it in a way that the connector is not only fixed to the PCB by the solder joint, so that the whole system is created in a way that we will be able to absorb these mechanical forces. And also the retention springs at the side are important to reduce that and to make sure that the mating part really slides in a correct angle in. Another point what we have to keep in mind when we speak about our PCB design is the thickness of the PCB. Well, we know that we are speaking about a high-speed connector what is able to handle really high frequencies, and the frequency signal what we are able to handle is affected also by the line impedance, and that means also by the line length. And that is the reason why you have to choose the right connector for the right PCB what you like to use in your application. So, for example, there's a different part number if we are speaking about a 1mm PCB compared to a 1.6mm PCB. And that will affect also the routing and the PCB design because of the signal. One big advantage of that type is that the mating part, or that the both parts, the PCB side and the plug side, we can use in both directions, like we can see here in that illustration. So it's a receptacle type, and that's that is a very big advantage for the user, because we all know the situation where we like to plug in our USB stick, and we try to plug it mostly first in the wrong way, in that it doesn't work. So everyone knows that. But with that type of connector, we will not have that challenge anymore. How does a connector look like, and what about the pinning? What we can see here is, this is a PCB side, just the front view, and we can observe directly that we have two pin rows, the row A and the row B, and every pin row we are speaking about 12 pins. And colored, you will see the different signals. So in red, we can observe that we find the standardized USB 2.0 signals. Added in blue, the additional information lines, and for the 3.1, we will find a CC1 and a CC2 when we take a look at the pin A5 or B5. That is a pin what will send a signal and recognize, okay, in which way is the mating part plugged in. So over that line, we will get the information, do we put it in upside down or in the other way. So the CC, it's a configuration channel, and the detection and power management. Well, for the power management, to transfer the power from one device to another one, we also have to choose, of course, the right cable so that the whole system fits together, but we will come back to that a little bit later. What we can see in that picture is the concept about the shielding and the grounding. So we have really additional grounding packs to protect our signals, that we can make really sure that we will get all the information what we transfer over that type of connection. And of course, to absorb the mechanical forces, here we have these dip retention pins, what gets soldered in a THR version to the PCB to be really able to absorb this forces when we plug in the mating part, also over the whole lifetime, the 10K mating cycles. And there's another point what we can see in that picture, that we have different pins. So here we have the THT pins, and at the back side of that connector we have the SMD row of pins. So that is a part where we have a mixture of both, but that's important to understand, because this will affect also the way and the length of the conductor what the signals are taking. And that means we have to respect that in our routing, that the running time of the different signals will be nearly the same, because we don't know in what position the end user will move in the plug. So how we can measure that, we will see later in one slide. Okay, and then we have to analyze the plug. The plug itself, we will see that in the B row of pins, pin 6 and 7 is missing. And pin 6 and 7 is still available for the A row. Why is that the case? Well, we know it's red, so that's the original data signal for the USB 2.0. And if we don't, so if the B6 and 7 contact will stay, we would just create a shortcut. So to avoid that, these pins are just removed in the plug, because the data plus and minus is only once available. Well, in the market, often I hear comments like, well, this is to recognize in what way the mating part is plugged in. But that's the information what's definitely wrong, because like I told you in advance, in which way the mating part is plugged in, we will recognize by analyzing the CC1 and CC2 signal. So that's the data where we transfer these kind of information. So we have to analyze the whole system. Here we see a picture of the cross-section view of the receptacle and the plug, how they are fitting together. And like we can see here in the real cross-section picture, that we have a massive construction design of this type of connector. So first we have the end lock, so the blocking system that you can't slide the contact deeper in, and that's important to define really the length of the signals, because when we imagine if the mating part would stay in like we see it here in that picture, it's a completely different signal wavelength compared to when you slide it in until the end. The next point is what we can really observe in this picture is, and that's very important, that's a grounding layer between the row A and row B. We all know that not connected or not used pins work like an antenna, and they can transfer and also receive signals, so that would destroy our whole speed if we would lose there some information. So the grounding layer is really important in that context. Good. Here we see when we try to analyze the RF behavior and when we measure a connector, we have to go a little bit backwards first to analyze how the system is working and how we have to set up our analyzer. So in that picture we can see a 4-port frequency analyzer, and when we measure the signals, it makes sense to measure only the signal way and not the measure lines. To be able to do that, what do we have to do? We have to use a calibration board that we can move the zero line to that way that we don't measure the test equipment together. So that is what we have to do first. And so the calibration board has to be connected. And that calibration board and also the design later, it's important that we have an impedance-controlled PCB. Why? Because otherwise the PCB manufacturers, they have factory tolerances what will affect so much the RF behavior that we can't use a measurement like that. And also for the end application, we have to make sure that every device is working in the same way. So we have to buy definitely impedance-controlled PCBs in case that we want to use the full speed of a USB 3.1C type. What we can see here is the equipment where we work with the end resistance with a 50 ohm system for the calibration board, and then of course we know for the line adjustment we have to analyze the behavior of the signal and of the lines. So here we see the Smith diagram. In a perfect calibrated world, we would see only a point, only one small point in the middle of the Smith diagram in the middle. But we know that we are not in a perfect world. So in that example, what I like to show you here, we have a correspondence line impedance of approximately 53 ohm. And then we have to compare also the Smith open, in that example 100 millimeter, and the Smith short, to compare them to each other that it works well. And by all the calibrations, we have to keep in mind that the SMR plug itself has also a defined length, what we have to reduce from the measured system. So the mechanical length is every time different. But here, like we can see, that the running time is really close to each other. Also the insertion loss for the reflection from open to short, what we can see here is that they are really yeah, now my English word is missing. We can see, was heißt denn gegenseitig? Okay, I use my mouse to explain that every time where we have a peak on top, so we have also a kind of valley at the other side for the open and the short. And this, of course, is affected by the frequency. So the insertion loss, as higher the frequency, is more loss, of course, we have. Here, when we analyze the test board, how we can do that, we will see that also the contact lines are not really straight. Why are we doing that? Because we have to make sure that they have all exactly the same length. And that's even for the receptacle version. There we have a difference between the SMD pads and the THT pads. So that's something what we have to keep in mind when we design a board. And there's one point what is where we are realizing that a lot of mistakes will be done there at the market, and that's the via preparation. It's important that the vias, when we design them in our PCBs, that we do it like we can see here at the right side, to avoid to have rest rings. So here we see at the left side these rest rings, and that's a standardized via what we can use in our PCB program. But there we have definitely capacitive and inductive influences. And to avoid that between the layers, we have to make sure that we are using a via where we have no rest rings. Of course, the line where we connect the signals, in that example, the bottom layer, there we need it. That means that we will reduce the mechanical performance a little bit. That's the reason why mostly the PCB designers recommend to have a rest ring. But here we have to keep still our RF behavior and our speed of the signal lines in mind. So in that case, it will disturb us. And then when we measure a system, it's nice when you contact maybe your connector manufacturer, and they will send you some S parameters of the connector, but what does it tell you? And that moment really nothing, because we have to measure the whole system from the via, from the first, or we can say from the entrance of the signal over the USB socket, over the plug, over the whole cable what we need. And the cable lengths can be completely different compared to the next plug, to the socket, to the via. So that's the whole system of the, or that's the whole way what the signals have to take. And that's important because we have to know if the speed or the traffic what we like to handle in our USB 3.1c system, that it works. And what we can see here is we can see how with a higher frequency that we have more loss of the signal. So here at one point we will be able to, or we will lose more and more information. So here in that example at around 11 gigahertz, so that will be the frequency. But that's still the third harmonic of the ground speed what we have for our USB 3.1 signal. Here we can see a comparison between the THT pins at the left side and the SMD pins at the right side, how the data lines or how the pairs of data lines are reacting. Like we can see here, if we have a PCB design, what is done in the right way, what is respecting the different pin lengths, that we have a nearly similar reaction affected by the frequency, of course. And then we have to analyze, of course, the crosstalk also by the changing frequency. How does it affect the other lines? And all these data, a good connector manufacturer will be able to handle you these real measured data to you. And there's one point by side of that seminar. There's a S2 Spice tool existing, and that helps you as a designer for your LT Spice model to implement the real measured curves. So you can implement them into LT Spice, but there's one point what we have to keep in mind. First, you have to download the S2 Spice converter. Here's the link in the presentation. And these S parameters has to be in the touchstone format, otherwise you will not be able to transfer that into your LT Spice model. Okay, so what we can see is that the USB 3.1c type is really a type where we are able to handle these higher data rates, even in the third harmonic of the frequency what is needed. And we are also able to handle these higher power supply current what we need, and also these mechanical parameters, like, for example, 10K mating cycles. And when we have these main parameters, so mechanical, electrical, and also the RF behavior in our mind, we would see that this is a connector what we can really use in nearly every application. in rough environmental applications. This is a connector what is designed for the industrial market, not for the consumer market where it's well known in the moment. And we can combine, because of the number of pins for that type of connector, also different protocols. So we can mix them up, for example. We can use a 2.0 signal, and we can mix it up, for example, with the I2C bus system. Or, well, all these PCI Express or DisplayPort connectors can be all reduced at our computers and our industrial devices in the future, only by using one standardized connector because of the connector specific characteristics. And when we analyze the speed, well, we are really able to handle 4K displaying and also additional power charging of our mobile device. So these are really, this is really a connector. When we analyze the different characteristics, that the question is not where can we use it. From our point of view, the question is really where it doesn't make sense to use it, and we will not find a lot of applications. So that was a small summary from my side. My colleague Elena Stark already showed me the time card, so I have to speed up a little bit. So we can use now the rest time to answer your questions. Okay, one question what we got is what different type of signals these connectors are able to handle. And well, we are a manufacturer of the connector, so we are analyzing the hardware performance. But for the different protocols, there is a good link at the USB side, where you see also from the USB organization proved software suppliers, and they will find the link what different type of signals are fitting together to one type of connector. Okay, then we have the next question. If we can put a Type-C connector on a USB 3.0 device. Well, in general, the connector you can use. You will not be able to use the whole pins because they are different. But from the connector itself, the Type-C is a connector what is able to handle much more. So in that way, yes, you can use it. For the power delivery mode, you have to make sure that the E marker of the cable fits together, that you are still able to handle these 100 watt of power supply for your devices or for your handheld where you like to use it. Then I see the question where you can find these S parameters and these models. Well, the easiest way is just to get in touch with us, write us a mail, and we can support you with the S parameter, even of that test examples what I showed you here in that presentation. So all these data you can receive by mail. That's no problem. Then we have the next question. Are there any guidelines for PCB layout pattern to the USB connector? Yes, they are, because the solder process in THR, you have to follow the recommended PCB layout pattern, but you will find them in every data sheet of every type of USB connector. And they will explain you the pad dimension and also the stencil thickness for your solder process. Okay, so we have no other questions, so I'd like to say thank you very much for joining this webinar, for your interest in Würth Elektronik and also in the topic about 3.10. If there are popping up some questions in your mind in the future, just feel free to contact us by mail, and we are really happy to support you in the best way like we can offer you. So from my side, thank you for joining that seminar, and I hope you will follow us on our webpage and on our channels. Thank you and bye-bye.